Okay, welcome to a lesson on oscillations, mathematics, and equations. All right, we're going to look at a couple equations and problems that model simple harmonic motion and oscillations. So the first one we're going to look at is an equation that relates or that talks about the period of a mass spring system. All right, we saw this in a demo where we talked about the frequency and the rhythm, if you will, of the mass on the end of the spring. And we figured out that the amplitude was not affecting the period. And you can see in our equations that A does not show up, all right? Now, the period we can see depends on the mass and the spring constant. Now, for this equation is not unique, but there's a special way of remembering this, all right? So for you Dalran people, we used to have a history teacher and assistant principal with the last names Tominski and Kaminsky. And one of my students came up with the idea of remembering this equation in that Tominski equals 2 pi times the square root of Mr. Kaminsky. So a nice easy way to remember that equation. All right, so let's look at a problem and see how we can use this thing. Okay, so we see what the problem is giving us, and we'll write that down quickly. The mass is equal to 0.15 kilograms, and the spring constant is 175 Newton per meters. So they're just asking for the period, and we know Tominski equals this 2 pi times the square root of Mr. Kaminsky. All right, so now we can just plug these numbers in. Period equals 2 pi, the square root of m, which is 0.15, this should say kilograms, 0.15 kilograms over 175. Now we can just go to our calculator, and that will give us 0.184, and the units is seconds, because remember, period is the time at which it takes to go one complete cycle. All right? So fairly straightforward question. Let's look at our next problem. Okay, now in this problem, they're giving us the same stuff they gave us last time, but this time they're looking for frequency. Well, we don't have an equation for frequency that relates to those. We have is our equation for period. But remember, the period and the frequencies are inverses of each other. So if we get period, we can get the frequency just by flipping it. All right, so let's go to our period equation. Tominski equals 2 pi square root of Mr. Kaminsky. The mass was 0.35 and the K was 250. All right. And if we go to our calculator here, this would just give us, let's see, I'll do this real quick, 0.35 divided by 250 equals the square root of that times 2 times pi, and we have 0.235 seconds. All right, and there's our period. So to get our frequency, all right, since these are inverses, we just flip this. We put this 1 over, all right? So T is equal to 1 over F. Therefore, F is equal to 1 over period. See how I flip both sides? So this would just go down here, and we get frequency equals 1 over 0.235. And I will do that in my calculator. There's a special button for that. Hit that one button, and we get 4.25 hertz. Now, what that means is that we'll make 4.25 round trips every second. All right, so it's 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. That's essentially the rhythm of that system. Okay, now let's move on to our next equations. Okay, so what we're going to look at now is equations that model simple harmonic motion, all right? It's an equation that tells us, it's equations that model the motion of something going back and forth, whether it's horizontal or vertical, all right? Now, we saw already that if we graph this motion versus time, it gave us a sine or cosine curve. Now, understand what this graph is telling us. This is telling x at any point in time, all right? So as we go through this thing, notice it starts at its amplitude, its highest spot, and at 1 second, it's at its equilibrium. All right, then I don't know, about 1.5 seconds, it's at its negative equilibrium. All right, so if you had to visualize this thing, there's equilibrium. It would start out here at 0, and by 1 second, it would be here at the equilibrium. Then it would go on the other side of the equilibrium all the way out to this spot, and then come back to the equilibrium at that spot, and then up by here going there. That's essentially the motion of that thing. All right. So once we see that, how do we translate this into an equation? All right. Well, let's figure that out. Okay, so if we continue looking at this graph, we see the shape is either a sine or cosine curve. They're essentially the same exact curve, it just shifted over a little bit. So you can imagine that where this thing is located is going to have the sine or cosine function involved, all right? And it does. There is our equation. Now, the big obvious one is, well, which one is it? Is it the one that involves sine or the one that involves cosine? Remember, they're the same shape, all right? So how we determine this is based off of initial conditions. In other words, where does the thing start? All right, so let's figure out those conditions now. All right, so let's look what I mean by initial conditions. All right, this line here is my initial conditions. It says if t equals 0 and x equals a. All right, what that means, what that would look like is if I stretch out the spring and let the mass go at its amplitude, all right? And that's when I start the timer. That's when I say time equals 0. That's when it starts. If I let it go from there, all right, what would that look like? Okay, so if we go to our x of t equals a cosine of 2 pi, f is in here, sorry, but it really doesn't matter. What this means when I put x of t, all right, if the t is 0, then that means every side on this, the t becomes 0. So here's our 2 pi ft. Well, that t and that t are now 0 on both sides. So once we multiply this whole thing by 0, we have a cosine of 0, and cosine of 0 is equal to 1. Well, 1 times a is equal to a. And what that's telling me is remember, x is its position, all right? Where is x when time equals 0? It's at a. And that was our initial condition. So this is the equation that proves that, all right? If I were to use sine here, all right, then if I were to use sine there, well, let's look at this other one here. We can come back to this, all right? And notice in this one, I changed the initial conditions. Now I said if at the start, when t equals 0, now it's not starting at amplitude. It's starting right at its equilibrium, all right? And what that would be is if when I start the stopwatch, I push it a little bit so that it travels out to A. It's not starting at A, it's starting here, but it's moving that way. So it's all about kind of when you're starting the timer. In this one, I'm starting the timer at t equals 0, and the thing is still at equilibrium. It hasn't traveled out here. So if we do that, t is 0, so 0 goes in there. So that means sine of 0. Well, what's sine of 0? Sine of 0 is 0. 0 times A does give me 0. And that's this position on, in other words, its position at time equals 0 is 0. So it depends on these two conditions, or the initial condition, on which ones you use. Let's go back to this one real quick and see if I would have done it wrong. If I would have done it wrong here, it would have said sine, if I were to use the sine equation, if I plug in 0 here, then I would get sine of 0, right? Sine of 0, and sine of 0 equals 0. Then I would have x of 0 equals 0. Does this statement fit this statement? This says at time equals 0, x is equal to a. That's where it starts. This, if I use sine there, it'd be the wrong one because it would be saying that x of 0 is at 0, and that would not fit. all right? So to figure out what equation to use, all right, it's all about these initial statements here. If it starts at equilibrium, which is x equals 0, all right, you use sine. You use our sine equation, which is 2 pi ft. Sorry about that. And likewise, or opposite, I guess, if we have these initial conditions where it starts at x equals a, it starts at its amplitude, then you use our cosine, and that's the rule. X of t is equal to a cosine of 2 pi ft. And that's how we know which equation to use. All right, so let's look at problems and put this into play. All right, so in reading this problem, they want to know what the position of this thing is at a certain point in time. So we have our equations, and we have to pick which one it is. All right, so by reading the problem, it says it is stretched out to the problem means its amplitude is 0.04 centimeters. All right, and that is when it's released. So at time equals 0, that's where it is. All right, that's where the problem's starting. It is starting at its amplitude. So when it starts at the amplitude, that means we use our cosine. X of t equals a cosine 2 pi ft. All right, now we can plug these things in. X, now look, what this means is whatever t that I'm concerned about, that's what that value goes here. So the t I'm concerned about is said at 1.5 seconds. So the amplitude is 0.04 cosine of 2 pi. The frequency they gave us was 7. And remember, this time is now 1.5. And we do this. So this whole thing here, this is the first time we've ever done this where we are not putting in degrees here, all right? We're not putting in 65 degrees. We're not putting in 90 degrees or any of those things. This is radians. So we have to make sure our calculator is in radians, which is no problem. So just this, I'll just do that. So you can check it on your calculator. 2 times pi times 7 times 1.5 gives me cosine of 65.97. And then we'll do in radians. All right, cosine of that in radians is equal to, actually, -1. So this whole thing here is equal to -1. So we say x of 1.5 will therefore equal -0.04 meters. And that's telling us where it's going to be. It's actually going to be on the other side at its amplitude. That's what the negative means. If it starts at +4 in 1.5 seconds, it will be at -0.04, be at the other side, and that's what that means. All right? So let's look at our next problem. Okay, so in this problem, it's very similar to the last one, except when we read it, our initial conditions are different. In this one, it's saying at time equals 0, it is starting initially at rest, all right? And it's given initial velocity, so it's at the equilibrium. It's a little bit hard to read, all right? But that's saying at t equals 0, it's x equals 0, starting at its equilibrium. When it starts at the equilibrium, that's our giveaway to use the sine equation. X of t is equal to a sine of 2 pi ft. They want to know where it is at what time. Let's see, looking back, it was at 2 seconds. All right. The A was 5 centimeters, 0.05. Sine of 2 pi frequency. What was the frequency? The frequency was 8. And remember, this time and this time is 2. So we do the sine of that whole entire thing. Remember, this has to be in radians. When we plug all that into our calculator, we see the position at 2 seconds will be, let me plug it into my calculator real quick, 2 times pi times 16 equals let's convert it into radians and take the sine of that times 0.05, and I will get 6. It's actually 6 times 10 to the negative 12 meters. So it's pretty much at its equilibrium point. It's just off there. It's a really, 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 really small distance from its equilibrium. All right? And that's how we do this problem. So let's look at one last problem for oscillations here. All right, so after reading this problem, we see that the system has a certain frequency when it has a displacement of that. In other words, it gives it, it lets it go at 3 centimeters. So the 3 centimeters is its amplitude. But then in the next part, they're going to say, well, what happens to the frequency if we stretch it out even more? Essentially, if we double it, all right, what will the frequency be? So you may think, well, if you think about this equation, T equals 2 pi times, Tominsky equals 2 pi times the square root of Mr. Kaminsky. Well, I didn't give you any of these things, so how can we figure this out? Well, you need to use your brain a little bit here, all right? The amplitude increased, so what happens to the period? The amplitude doubled, so what happens to the period? And the answer is nothing changes. Amplitude does not affect period. It does not affect the rhythm. It does not affect the frequency. We saw this in demos, all right? So the answer, what is the frequency of the system? All right, the frequency of the system is still 5 hertz, just like it was when it was at 3 centimeters, all right? So don't be fooled by that, all right? Trust the science, believe in the science, don't rely on your own program. Trust science. That should be a big time theme of not only your life, but how society should work too. So, learn these things. It helps to be science literate and understand how to use these things. Okay? So, thanks for watching, and see you when I see you.